Okay, November 19, paper 6, variant 1. Question 1. We have a beam or a meter ruler. We have a meter ruler and we have two distances. Distance A is the distance between the center, okay, the center of the ruler or the whatever you might name it. Okay, center of the ruler and the pivot. This is distance A. And distance B is the distance between the pivot and the center of mass P. Okay, so we have two distances, A and B, and P is actually at the 90 centimeter mark. P is fixed at the 90 centimeter mark. A is always the distance between 50 and the pivot. Okay. Um, in the table, he's asking me to calculate and record the distance B between P and the pivot. And then I'm required to find A over B. How can I find P? How can I find B? How can P is already at 90? How can I find B? If you think about it, if you think about it, you'd find that the distance between A and B, or the distance A plus B, if you always add A plus B, the distance will always be what? The distance will always be 40. If you find A plus B, the distance will always be 40. Why? Because A starts at 50 and B ends at 90. So the distance between them is always what? Is always 40 centimeters. Whichever distance is A or whichever distance is B, whenever you add both of them, the distance will always be 40. In the table, can I find B? Yes, I can find B. Why? Because to find B, all you do is subtract 40 minus 23.1. 40 minus 23.1. So 40 minus 23.1 is 16.9. 16.9. Okay. Can I find A over B? Yes, I can find A over B. All we do is divide. Okay, we just need to divide A divided by B. 23.9 divided by 16.9. Yeah, 23.9 over 23.1 over 16.9. Over 16.9. Which would give you a final answer of 1.37. 1.37. Okay, not bad. Moving on to the next question, he wants me to plot a graph of P slash N on the y-axis. So first of all, I need to label the y-axis, P slash N, and then A slash B, or A over B on, it's not A slash B, it's A over B. Okay, it's unitless actually. Okay, there's no unit for A over B. You do not need to start the axes from 0 and 0. I'll not start the axis from the origin. Actually, if I do start it from the origin, it would be wrong. Okay, can I fill out the numbers? Yes, I can. Let's start off with P. P starts from 0 0.5 and ends at 1.5. Okay, so if I start off with 0 0.5, can I go up with increments of zero point 0.5, for example, 0.5, 1, and 1.5? Definitely that would be wrong. Why? Because I will finish all of my numbers at this point, which is wrong because I need to fill up more than 60 or 70% of the graph. What would be a suitable increment for the numbers on the y-axis? A suitable increment for the numbers on the y-axis would be zero point 0.2. Let's try it out. Let's try it out. Zero point 0.5 and then you add zero point 0.2 is 0.7. If you added another 0.2, 0.9, 1.1, 1.3, and 1.5, which is excellent. Okay. Someone else might add 0.25, which is not wrong. Again, 0.5, 0.75, 1.0, 1.25, 1.5. Again, it's correct. But the problem with an increments of 0.25, that the differences between them would be much harder. differences between them, and we're trying to find very small differences, okay, it would be much harder. Point two is much easier to find the differences. It's much easier to find the points on the graph if you have point two or point one. Now, can I write down the numbers for A over B? Yes, I can. It starts off with 0.455 and ends at 1.37. So maybe I can start off at 0.4, 0.400, and end up at 1.4. End up at 1.4. How can I do that? By increments of, again, 0.2. Let me zoom in. If I start off at 0.400 and increment with 0.6, 0.2, next number would be 0.600, and then 0.800 and 1.00, then 1.2, okay, 0.4, 0.6, 0.8, 1.0, 1.2, and 1.4. Would that be correct? Yes, that would be okay. That would be excellent. Okay, 1.40. On the y-axis, each small square would be zero point zero 0.02. Each small square would be 0.02. And on the x-axis, each small square would be also zero point zero 0.02. For example, 0.5, the next small square is 0.52. Next one is 0.54, 0.56, and this is 0.6. On the x-axis, 0.400, 0.420, 440, 460, 480, and then 0.500. Okay, so on both axes, which is out of pure luck, that both axes have increments for the very small squares of 0.02. It's not always like this, but it's quite lucky. We're quite lucky for this test. طيب. Let's start. Yeah, let's start plotting the points. I'll start from 0.45 and 0.5. So 0.455 is almost 0.46, isn't it? It's almost 0.46, and this is 0.5. So 0.46 on the graph, okay, would be three squares from 0.5, 0.46, and 0.5. Again, we're plotting using small x's. We're plotting using small x's. Okay. Um, Next point, 0.724 and 0.8. 0.724, we can just plot it at 0.72, okay, and 0.8. 0.72. Where's 0.72? This is 0.7. Next square is 0.72. We can move up to this point, which is the center, 0.8. This is 0.8, and this is 0.72. 0.72. Next point would be 0.9 and 1.0. I guess this is the easiest one. 0.9 and 1.0, which would be at this point exactly. Yeah, this point exactly. 0.9 and 1.0. Next point is 1.13 and 1.2. 1.13 and 1.2. 1.13 is 1.1, 1.12, 1.13. And he said what? And 1.2. Okay, 1.2, that's easy. Okay, 1.2 is here, so this would be the point. Small x's. Okay, we're using very small x's to plot the points. And last but not least, 1.37 and 1.5. 1.37 and 1.5. Where's 1.37? It's just before 1.4 and 1.5. Yeah, this is 1.37 and 1.4. So these are the points. Let me zoom out. Yes, these are the points. Can I draw a line of best fit? Yes, I can draw a line of best fit. Okay, let me use this line mm, with a different color. It would be somewhat like this. Okay, actually, this would be a really good best fit line. Why? Because all of the numbers are very close to the line. You have one or two numbers, one or two points above the line, one or two points below the line, which is equalized. This is what we call a line of best fit. Okay, this is a really good line of best fit. Okay, so your line of vested should look somewhat like this. And the next question, he's asking me to find the gradient. Okay, I will not scroll down now. Okay, next question, he is asking me to find the gradient. To find the gradient, you need to use the triangle method. How can I use the triangle method? On the graph, again, you need to draw two lines. On the graph, you need to draw two lines. You need to draw the triangle method to find the gradient. I'll use the two furthest points away. Okay, for example, this point along with this point. And basically, you need to find the rise over run. How can I find the rise over run? Okay, to find the rise over run, which is y2 minus y1 over x2 minus x1. Okay, which is y2 minus y1. Okay, y2 is 1.5 minus y1, 0.5. X2 is 1.37. Okay, 1.37 minus 0.455. Okay, I guess this was 1.1, but let me calculate it again. Over 1.37 minus 0.455. Yes, exactly. The gradient would be around 1.1. Someone's asking, can you explain A over B again? Okay, can you explain A over B again? A over B, basically all you did is you found the values from the table, okay, the values from the table, and you divided A divided by B. And just A over B, A over B for all of the values of A and all of the values of B. That's all you did. Okay, you just divided all of the values. Okay. Um, Good. To find B, if that's your question, to find B, again, all I did was 40 minus A. Why? Because the difference between A and B is always, or the summation of A and B is always 40. To find B, all you did was 40 minus the value of A, um, and we found B. Okay? Okay. Let me move on. I guess yes, I need to move this. So G was 1.1. We calculated G. It was 1.1. The gradient is numerically equal to the weight. The gradient G is numerically equal to the weight W of the ruler. Can I write down W? Can I write down the value of W? Yes, it's numerically equal to G, meaning that W is G, 1.1. But I need to include the unit. What is the unit of the weight? What is the unit of the weight? Unit of the weight is newtons. Unit of the weight is newtons. Yeah. The student has assumed that the center of mass of the meter ruler is 50 centimeters, is at the 50 centimeter mark. Explain briefly how would you find as accurately as possible the position of the center of mass. Okay, how would you find the center of mass if it's not exactly at 50? How can I find the center of mass? All you need to do is what? You need to just simply remove the mass and start to balance the ruler without the mass. Start to balance the ruler without the mass. So simply remove the mass and balance the ruler without the mass. Yeah, remove the ruler and balance it without the mass. Briefly state the main difficulty that you would have when carrying out this experiment. Okay, one of the I told you before, we have only four difficulties while dealing with this experiment. And the main difficulty while dealing with this experiment was what? The main difficulty was actually obtaining a balance, was balancing the ruler. There is a huge difficulty. Okay, there's one very important difficulty, which is actually balancing the ruler. So there is a difficulty in balancing the ruler. Balancing the ruler. Okay, this is a main difficulty that we face while actually trying to conduct this experiment. The ruler isn't always balanced. Okay. Hmm. Yeah. She's investigating the resistance of lamps. She needs to find the resistance of lamps. I have lamp L1 and then I have an ammeter and a voltmeter. Can I take the readings of the voltmeter and ammeter and then find the resistance? Yes, I definitely can do that. What is the reading of the voltmeter? The reading هنا is 2.2, 2.4, so it's in between 2.4 and 2.6, which is 2.5 volts. What is the reading of the ammeter? Huh? This is exactly between zero point 0.2 and zero point 0.4, which is 0.2, 0.3, 0.3 amperes, 0.3 amps. Can you find the resistance R1 of the lamp using the equation? Yes. Yalla, equation 2.5 divided by 0.3. R1 would be 8.33. Again, what is the unit? Do not forget the unit. Ohms. 8.3 ohms. Okay. Hmm. I have a new value. Soon connects L2 in series. When he connects L2 another lamp in series, he found V2 and I2. Can I find R2? Yes, I can find R2. 2.4 divided by 0.21. 2.4 divided by 0.21, which would give you a reading or a resistance of 11.4. Again, do not forget the unit, 11.4, and the unit is ohms. She connects lamp L3 in series with lamp L1 and 2, V3, I3, and R3. And then a student suggests that the resistance R3 of the three lamps in series should be given by the equation 3 R3 equals 3 times R1. Okay, he is suggesting that that these three lamps are equal. These three lamps are of equal resistance, and that if we have the resistance of one lamp, which is R1, we could just multiply 3 times R1. We would find the resistance of the three lamps together. Would Is this statement correct or not? That's the question. Is the statement correct or not? Let's calculate it. 3 times R1. What was R1? 8.33. So 3 times 8.33 would be 24.9. And R3 is 14.1. Are they equal? We need to find out. 24.9 24.9 divided by 14.1. The larger number divided by the smaller number. Okay, the larger number divided by the smaller number. So 24.9 divided by 14.1 is what? 14.1 is 1.76 or 1.77. Okay, it doesn't actually matter. Okay, 1.77 or 1.76, which is 77%. There is a 77% difference. Definitely they are not equal. So the statement would are we going to say they're equal? No, they're definitely not equal. Statement, no, not equal. Why? The justification. In the justification, we need to state the accuracy صح the experimental accuracy, are they within or not within the limits? So the numbers are far apart. In the justification we need to say that the numbers or the values are far apart, exceeding or not within, okay, exceeding or not within the limits of experimental accuracy. Yeah, the limits of experimental, okay, accuracy. Limits of experimental accuracy are usually within 15%. Okay, so if the value is 1.12, 1.13, if you divide the larger number by the smaller number, and the value is 1.13, 13% acceptable, up to 15%. At 15%, you could say yes or no. Actually, at 15%, you can say yes or no. Hmm. Yeah, complete the figure diagram to show three lamps in parallel. The voltmeter connected to measure the potential difference across the three lamps. A variable resistor to connect the current in all three lamps. Okay, three lamps parallel, a voltmeter and another um, variable resistor. First of all, the variable resistor will control the current in all three lamps. It will control the current in all three lamps. So first of all, we need to add the variable resistor. Okay, first thing. Then we need to add the three lamps in parallel. Yep, one lamp, two lamps, and three lamps in parallel, in addition to the voltmeter, which should be also in parallel. Can I draw the voltmeter first before the three lamps? Yes, you can. You can switch the position of the first lamp with the voltmeter, or any lamp, in fact. You can, uh, as long as the voltmeter is connected in parallel to these three lamps, then it is okay. Um, they will all have the same voltage, the same potential difference, as the they will all have the same potential difference. Hmm. Yep. A student investigates the cooling of water. The cooling of water. Hmm. Can I take the reading of the room temperature theta R? Yes, I can take the reading of this room temperature, which is 24 degrees Celsius. 24 degrees Celsius. The student pours 200 centimeters cubed of hot water in the beaker. He places the thermometer in the water. He measures the temperature every every 60 seconds. Every 60 seconds. So to complete the timed column in 3.1, can I complete the time column every 60 seconds? I'll just add 60. 0, then 60, 120, 180, 240. Ah, you just add 60. And then can I complete the column headings? Yes, I can complete the column headings. The time is in seconds. He said every 60 seconds. What about theta? Theta is the temperature. Theta is the temperature, so degrees Celsius. Degrees Celsius. Can I find the decrease? يلا. Can I find the decrease in the temperature delta theta 1 in the first 120 seconds? In the first 120 seconds, يعني from 0 to 120, can I find the decrease in temperature? Yes, I can find the decrease in temperature. From 0 to 20, we started at 95 and we ended at 85. So basically the delta theta, the change in temperature is what? يلا. 95 minus 85, which would be 10 degrees Celsius. Can I find the decrease in temperature during the last 120 seconds? Yes, I can find it during the last 120 seconds. I started at 120 and ended at 240. 120 seconds. So 85 minus 78, which is 7 degrees. 85 minus 78, which is 7 degrees Celsius. Guess it's easy up to now. Hmm. Tick the box to show your conclusion from the results in C. The average rate of cooling is greater in the first 120 seconds than the last 120 seconds. Least is less or is the same. Hmm. I don't think it's the same. It's not the same. I guess it's greater in the first 120 seconds. Why? That's the justification. We need to write down the justification with the numbers. With the numbers. So delta theta 1 in the first, okay, in the first 120 seconds, delta theta 1 was equal to 10 degrees Celsius. In the last 120 seconds, delta theta 1 was equal to 7 degrees Celsius. So is there a difference? Yes, there is a huge difference. Okay, which is much greater. Okay, delta theta 1 is much greater than delta theta 2. Is greater than delta theta 2. Hmm. Okay, yeah. Suggest two ways in which the student could reduce the rate of loss of thermal energy. How can he reduce the rate of loss of thermal energy? In this question, he had a beaker, he had some water in the beaker. Hmm. How can I reduce the rate of loss of thermal energy? Using, yes, using insulation. What do I mean by using insulation? If you have the beaker, can I wrap it with some wool or with some cotton or with whatever insulator, some sort of insulating material? Yes, I can do that. So wrap it, okay? Wrap the beaker with an insulating material. Yeah, insulating material. Hmm. What else can I do? Can I cover the beaker with a lid? Yes, exactly. I can use a lid. So use a lid. Definitely, the lid would affect the rate of cooling. It would decrease the rate of cooling so much. Okay? Okay. Hmm. Next question. Draw a diagram of a measuring cylinder being used to determine the volume of water. Being used to determine. Someone saying, can we use a shiny material? Okay. Well, the question is asking you to deal with the beaker that you have. You already have the beaker. Type. This beaker has whatever color, which is usually glass, so it's kind of colorless. So coloring the glass wouldn't affect the rate of cooling that much. It would, it would affect, okay, it would, but not that much, not that much. The lid would definitely affect it way much more. The insulation around trapping it with an insulation would affect it way more. Someone might say increasing or decreasing the initial temperature or the volume. These are all factors that might affect the rate of cooling much greater than coloring it shiny or whatever other color. Okay, so the color, yes, I know it should be taken into consideration, but in this question, there are many other factors that do affect the rate of cooling much greater. Okay, yeah. Hmm. Can I draw the diagram? Can I draw a diagram of a measuring cylinder and see how can I take the reading clearly? Yes, I can do that. Yeah, let's do it. Okay, let's do it. The diagram, the measuring cylinder, you should draw a measuring cylinder. You don't need to be very accurate. Okay, this is somewhat a measuring cylinder. Okay, this is a measuring cylinder. And we have the water. The water inside the measuring cylinder will always curve upwards. Okay, the water inside the measuring cylinder will always be curved this way. This is the water inside the measuring cylinder. How can I take the reading of this water? We always said a perpendicular and from the bottom of the meniscus. So at this point, you need to draw a straight line, okay, from the bottom of the meniscus and draw an eye at this side. So we say from the bottom of the meniscus and perpendicularly. Why? To avoid the parallax error. Two very, very important precautions while dealing with a measuring cylinder. From the bottom of the meniscus and perpendicularly. And perpendicularly. Yeah. Okay. So you have the measuring cylinder, you have the water level, and you're taking the reading perpendicularly. Hmm. Okay. Question 4, last but not least. Planning an experiment. A student is investigating the time taken for metal balls to stop moving after being released from on a curved track. You have the metal ball, we will release it. You will release the ball on this curved track. Figure 4.1 shows the shape of the track. The track is flexible, so the shape of the curve can be changed. Can be changed, okay? You can change it. The following apparatuses is available. You have some masses, you have some clamps, you have a flexible track, tape measure, a meter ruler, and the student can also use other apparatuses and materials, okay, that are usually available in the school. Usually available in the school or in the laboratory. Plan and experiment. Plan and experiment. Again, the most important statement you have to read, okay, while solving this question. Plan and experiment. To what? To investigate a factor. To investigate one factor. One factor. So for this question, it's up to you to choose a factor. It's up to you to choose this factor that affects the time taken for the metal balls to stop moving after being released on the curved track. So you have the ball. At this point, you leave the ball. It will start moving up and down. It will oscillate for a while and then it will stop. So you need to calculate the time taken. Okay, you need to calculate the time taken for the ball to stop moving. To stop moving. What is one factor that can be used? Someone is saying the initial speed. The initial speed might be wrong for this question. Why might the initial speed be wrong? Because you're actually releasing the ball. You are releasing the ball. You're not pushing the ball. You're not adding any force to the ball. Not adding any force to the ball. Okay, so the initial speed is always zero. In fact, the initial speed is always a zero. What is one other factor that might affect the time taken? Someone is saying the mass of the ball. Yes, that is correct. The weight, yes, definitely. Both of them are correct. Mass or the weight. Okay, mass of the ball, the weight of the ball. What else can someone say? For example, if you want to think about it, I will use the mass of the ball. Someone else might say, what about the position from which the ball starts? Instead of starting at this position, can I start from this position? Yes. Can I start from this position? Okay. If you want to change the position and find if it would affect the time taken for it to stop, okay, it's up to you. Again, this is it's up to you to choose one factor that might affect the time taken. Someone might say, can I change, for example, the material of the ball? Yes, you can change the material of the ball. So you have some factors from which you can choose. For this question, it's up to you. For me, personally, I'd prefer to use the mass of the ball. Why? Why? Because the mass of the ball is the easiest to change. How so? If you remember, if you recall, we have 7 steps we need to write down. Okay, you have 7 steps you need to write down. First of all, okay, if you don't have this page, you can just bring a piece of paper and start to write down. First of all, we need to write down what? We need to write down the range of values. What are the range of values? What are the numbers we'll be using in this experiment? The range of values. Range of values. What is the independent variable that will be changing? For example, I said personally, I'd prefer to change the mass. So the mass of the ball. Okay, what are some suitable masses for this ball? I can say, for example, 20 grams, 40 grams, 60 grams, 80 grams, and 100 grams. Some suitable masses for this ball. Range of values. If you go for example, the material of the ball, you need to state five different materials, whatever materials. Someone would say iron, someone would say glass, plastic, polythene, whatever, rubber. Okay, but they would all have the same what? They would all have the same mass. They would all have the same mass. So the range of values is the independent variable that we are changing. And then we need to state the controlled variables. The controlled variables. What are the constants? What are the constants in this question? The constants in this question. First of all, the material of the ball. The material of the ball. Okay, the material of the ball. Material. Yes, the position from which you release the ball. Position from which the ball is released. طيب. The volume, no, we cannot say the volume. Why? Because if you have the same material, if you have the same material, then as you change the mass, the volume will change. صح? Density equals mass over volume. You have the same density. So if you increase the mass, the volume will also increase. So volume is not one of the controlled variables. The volume is not one of the controlled variables. Let me tell you about one important controlled variable you'd need in this question. In this question, you can change the shape of the curve. The tracks is flexible. You can shape the curve as you like. So the shape of this curve needs to be constant. The shape of this curve needs to be constant. The shape of the curve. Okay? Hmm. Third point, we needed to state any extra apparatuses will be using the balance. Is the balance written down? Let's check. Meter, ruler, tape measure, stopwatch. We do not have the balance, so probably we would need to use the balance. So an extra apparatus would be using a balance. We already have the stopwatch, so we do not need to write it down again. Okay, you have the balance. We have the meter ruler to check the exact position from which we will release the ball. Apparatus, and then we need to write down the steps. What are the steps that we will be using? The steps. Release the ball from a certain position. Release the ball. Release the ball from a certain position. From, not form, from from a certain position on the track, or a fixed position on the track. From a fixed position on the track or on the curve. Start the stopwatch. Yes, start the stopwatch. And then calculate the time taken. The time taken for the ball to come to rest. Okay, you need to measure the time taken for the ball to come to rest. Then you need to stop the stopwatch, and that's it. That's all you do. That's literally all you do for this question. You just leave the ball from a certain position, take the time taken, or measure the time taken for the ball to stop, and then that is it. And then I guess we need to draw a table. Let me check the points. State how we, okay. Explain, state the variables. Okay, you need to draw a table. Like, you can draw the table in this empty space or on the lines as you like. Okay, it's up to you. If you have some space on the lines, you can draw the table here. If you don't, then simply draw it in the empty space above. This is the table. What should we draw in the table? What should we write in the table? We need to write the table headings. We need to write the column headings, and that's it. What are the column headings we need? First, we need the independent variable. We need the independent variable, which is the mass. Which is the mass. Excellent. Thank you. Okay, first of all, we need the mass, which is in grams. What are other variables that might change? The only other variable is the dependent variable, which is the time. So mass in grams and definitely time in seconds. That's it. That's all you need to write down in this table. Mass in grams and time in seconds. Okay? You measure the time and you measure the mass. That's all you do for this question. Okay? And then range of values, apparatuses. Can I write down any precautions? We don't actually need any precautions for this question. If you want to state some of the precautions, such as resetting the balance and resetting the stopwatch before using them, definitely this would be okay. Okay. Um, After stating the precautions, if you'd like, that's if you'd like, we can say the conclusion. Okay, the conclusion. Okay, conclusion. Steps and I release the ball and find the fixed position. Start the stopwatch. Calculate the time taken for the ball to come to rest. It will keep on moving back and forth. Okay. Conclusion. Conclusion. For each mass, yalla, we said the conclusion is rather static. Okay, for each mass, because this is the variable we're changing. Repeat the experiment and take average. Repeat the experiment and take average. Record the results. Record the results in the table. And last but not least, you need to compare the results. Yeah, compare the results using a graph. Compare the results using a graph. So for each mass, repeat and take average. Okay. Uh, Record the results in the table. Record the results in the table. Compare the results using a graph. Okay. Hmm. All good.